On the screen.
The title of my talk is Spacetimes containing quantum black holes and black holes containing quantum universe. This talk is about the results which are contained in this paper, which we called Quantum Oppenheimer, Schneider, and Quantum Shift Models, a paper written jointly with Professor Ma, with Professor Yang, and with Dr. Song. I hope that some of them are, or all of them maybe joined the lecture, and they can also make some comments when it's necessary or when they want. There is a debate in community working on quantum gravity. What is the relevance of the quantum effects which possibly take place in black hole, behind the black hole horizon, close to the singularity? So what are the effects that can be visible outside when we live in space-time, that is, as usually we do, that is on the other side of the horizon? So there are several people started with speculations and then continue providing some more specific models. But first, quite speculative paper was by Ashtekar and Boyovald, and then they proposed that the way we should look at this problem is as follows. So this is some collapsing matter. Collapsing this, there develops would-be horizon. So this is that trapping horizon, which normally would become a black hole horizon. However, due to some quantum effects inside, so this is region when metric tensor doesn't exist because we need some other quantum description. And then there is a bounce, some collapsing matter bounces, and then after bouncing, it expands. So this horizon disappears, and we see matter and a lot of stuff going out of what originally was going to be a black hole. Rovelli and Haggard made it very brutal and much more specific. Namely, they said, okay, so outside the horizon, space-time should locally look like Schwarzschild, because why shouldn't it? So suppose that space-time locally looks like Schwarzschild, so we can take various copies of Schwarzschild, we can do some surgeries, we can cut them, and then we can glue them in a different way. Because Schwarzschild is in some regions, or Schwarzschild is symmetric with respect to flipping t into minus t. And then they glued the pieces of Schwarzschild in such a way that this is a smooth Schwarzschild space-time. This is the horizon of, I mean, this is not the horizon of the resulting space-time, but this is what was the horizon of in Schwarzschild space-time. However, then it is glued with another piece of Schwarzschild where horizon is here. So we may say that if we live here, then we think, we are just, there is a black hole and nothing is going to happen. We don't get too close. However, at some point, black hole becomes white hole. And they even call it black hole to white hole transition. So we have tunnelings from black holes to white holes. So the idea is that every black hole which we can see is like a bomb, which at some point will turn into a white hole. And the rules of quantum mechanics or quantum gravity tell us when it is going to happen. So this is this other the other conjecture, which is
the corner, cross section of two, correct?
This is mathematically speaking, this is where we cannot glue properly the spacetimes. Physically and heuristically, this is this quantum region where the notion of metric tensor is replaced by some non-commuting operators, and the notion of manifold and a metric tensor doesn't make sense. Okay, let us continue. Let us see what are other bets about this structure. So another possibility is quite different, is the following. It's also by Ashtekar and his Olmedo and Singh, his collaborators. And this picture is actually a result of very long, very careful calculations within some quantum model. But the result of the calculations is as follows. So if we consider this effective, this semi-classical spacetime which emerges from quantum theory, then it looks more or less like the Kruskal spacetime. The only difference, qualitative, is that instead of the singularity, we have actually a bounce. So spacetime is regular here. There is no reason to end. Spacetime doesn't end. So we can just glue several copies of this regulated Kruskal diagram in this way, and we obtain sort of maximal extension of this quantum extension of the Kruskal diagram. So
Kruskal diagram, but I understand you have just in mind just the standard general diagram of Schwarzschild black hole, right? Or is it something else? This region 3, 4 W and if it's just a standard, that is just a standard black hole spacetime.
well, Kruskal diagram is this whole thing. So Kruskal diagram consists of bifurcated horizon, which has all the branches which are extended. So originally they're extended from minus to plus infinity. It contains this asymptotically flat region, the other asymptotically flat region, the trapping region, anti-trapping region, white hole horizon, black hole horizon. So whereas just standard black hole diagram, it would be only a part of it. It would be only right part when matter collapses and we develop. So Kruskal diagram is maximal extension. Suppose there is no matter. Okay, Kruskal coordinates. Okay, Kruskal extension of Schwarzschild spacetime.
So this is maximally extended spacetime.
Okay, guys, I'm going to tell you something interesting, something you don't know. Let us not argue about something what you guys know.
And the name.
I'm quoting somebody else's title of somebody else's paper. I don't know why people exactly called it quantum extension of the Kruskal spacetime. Given spacetime which is not complete, you can introduce your coordinates and extend it, and then they will call it Kowalski-Glickman spacetime. Okay, there was guy Kruskal who did it, and they call it Kruskal spacetime. Kruskal spacetime really describes black holes. You are absolutely right. It describes black hole. Yes, very good. Yes. Okay, so here you can see, but what is important here, that in the previous guess, we had a black hole which turns into a white hole. In this case, if we are, say, here in asymptotically flat region, we can see that black hole forms. This is a black hole horizon. However, we never see this black hole turning into a white hole. We may see this as a usual Kruskal spacetime with singularity here, and we don't, unless we jump inside, we are not going to see this white hole. So this is qualitatively different picture than this. Here, black hole turns into white hole. It's called black to white transition. This is also a brand name given by Haggard and Rovelli. While here, this white hole emerges in some different, asymptotically different regions. So we are not going to see this white hole. So there is question which picture is true, which we want to believe in. There are other works in which people apply some sort of Oppenheimer-Schneider model. This is what I'm going to be doing. So I will discuss it in details later. And there was a guess by the result by Michał Bobula at Lux 22, and this is from the slides of his presentation, which is that here is black hole horizon, then there is some complicated structure inside, and then there is again one asymptotically flat region, another asymptotically flat region, and according to this, we are not going to see, being in one asymptotically flat region, we're not going to see the white hole. So this belongs to this models in which black holes, there is no black-white transition. So in conclusion, there are two possibilities: black-white transition or black hole in one asymptotically flat region, possibly white hole in some other world. Okay, since I'm going to use the Oppenheimer-Schneider model, let me also mention that for a long time, people in literature write papers about possible quantization of Oppenheimer-Schneider model. So I will just give credit to some papers. I'm not going to introduce the results, but I was very happy when I saw that Włodek is one of the pioneers of the quantum Oppenheimer-Schneider models. So all those models, they bring up the idea of Oppenheimer-Schneider, where we glue to spaces some collapsing matter and Schwarzschild outside. However, we do it in the context of quantum gravity, either where collapsing spacetime is either really quantum or is some semi-classical in the sense that is described mathematically by continuous metric tensor. However, this metric tensor is not the original, but it already knows about quantum effects, and it satisfies some quantum Einstein equations instead of the Einstein equations. So let us remind what is the classical Oppenheimer-Schneider model. So consider homogeneous isotropic ball of dust, and suppose this ball is surrounded by spherically symmetric static metric, and it collapses. So as the ball collapses, the space-time which is occupied by the ball is described by a contracting. It may be depending on what kind of model we use, but in our case, it will be flat Lemaitre, Friedman, Robertson, Walker space-time universe filled with dust. On the other hand, outside, we are going to have Schwarzschild space-time, and the surface between the two solutions, it is the surface of the ball, and on this surface, space-time is continuous and once differentiable. So it is not twice differentiable because the stress energy tensor depends on second derivatives, and stress energy tensor here is 0 and here is not 0. So clearly there has to be jump in second derivatives. But assuming that there is no jump in first derivatives is something which is reasonable to make, and this is exactly what is satisfied in this Oppenheimer-Schneider model. And we know that this at some point horizon develops and the matter collapses to singularity, and at the end we obtain a space-time where if we are outside the horizon, we even don't know what happened, but we see that this is a space-time or described by the Schwarzschild metric.
You can do it analytically, classically, right? Can be solved for the standard data, can be solved analytically. Yes.
Yes. Yes. Everything here is analytic. This is Lemaitre-Friedman. Inside is Lemaitre-Friedman, Robertson-Walker. Outside is Schwarzschild. Both are given by analytic expressions. Okay.
Analytic in the sense of exact, not in the sense of smoothness, right?
No, you accept permanence.
Okay. Excuse me. I first take back something what I said, and then I will listen to the question. So in physics, or in science, we use the word analytically in two meanings. One meaning is analytically versus numerically. So if we are able to write expression in terms of elementary functions, then it means we did it analytically. If we do numerical calculation, then we do numerically. Another meaning is the meaning in the sense of analytic functions versus smooth functions or differentiable or non-analytic. So this solution is not analytic because it is only C1 on this surface. However, is it numeric? No, it's not numeric. It is written explicitly by analytic functions, which are matched along some surface in non-analytic way. Okay. Okay. Now there was a question from the Zoom.
It wasn't a question. It was exactly this comment.
Okay. Thank you. Thank you.
So I have one more comment. If you assume that the first derivative, have jumped, then you end up with something which is called shell.
Okay.
Metal shell.
Yeah, but I will
Then
not
get
talk about shells.
delta.
Yeah. Yes, that's true. There is also an interesting class of solutions, and now those solutions are also quantized, and also they were quantized earlier, and they also give a lot of material for speculations on quantum gravity. Okay, so now let me explain certain mathematical lemma which is behind the Oppenheimer-Schneider model. Okay, I was going to split it into several steps, but I didn't. Consider the following setup. Suppose that we fix arbitrary spatially homogeneous isotropic spacetime of this form. In other words, suppose that this function A is arbitrary function of variable tau. Okay. Here I wrote it in spherical coordinates because we will be connecting this with spherical symmetric spacetime, but it could be dx squared plus dy squared plus dt squared. So consider arbitrary metric tensor of this form with arbitrary function. And now consider arbitrary spherically symmetric static metric outside. And suppose that on the surface between the two regions, metric tensor is so the surface by definition is radial, so it is given by r tilde equal constant. And in the meaning of the metric tensor inside, the surface is determined by is generated by time-like geodesics or by so-called co-moving observers, by world lines of co-moving observers. And so this is the first assumption. And second assumption is that the metric tensor is continuous and of C1 class at this surface. And now the statement is that in this case, given A, the spherically symmetric spacetime outside is determined. We can actually calculate it, what it is in terms of A. And now miracle happens if we put inside the Lemaitre-Friedman-Robertson-Walker spacetime, then outside we will obtain Schwarzschild. If we add cosmological constant, then we'll obtain Schwarzschild ds or Schwarzschild ads. So if the space-time inside satisfies Einstein equations, and I mean, this is not general statement, but at least in those cases outside, we obtain a solution to Einstein equation. Oh, because this first part of the statement doesn't bring up Einstein equations at all. So for arbitrary function, well, okay, arbitrary, probably it's better if this function is in some sense homogeneous. So it's monotonic, or say that is a local statement. Maybe it works the best if function A is monotonic. If it's not monotonic, then we have to if it was oscillating, then maybe there could be some problem. However, locally there is this one-to-one correspondence, and Einstein equations have nothing to do with this. And maybe there exist some other equations in nature which should have to do. I don't know. But however, here we don't bring up Einstein equations. However, if we put here the solution to Einstein equations with dust, then on the right-hand side, this mechanism gives us also a solution to Einstein equations, which is empty. So even the rule is not clear, because inside we have solution with dust, and outside we have vacuum solution. So there is some magic in this.
Between this time here and power.
No, it's not. No, this is part of calculation which you do.
Maybe it's not geodesics, but they are internally geodesic, externally geodesic, or both.
So to start with, as they are given, they are geodesics with respect to the internal metric.
What about external?
And then, in the consequence of our assumptions, the external metric has to be determined in such a way that they become also geodesic with respect to the external metric. So it becomes one of the junction conditions. Okay, so we have this nice mathematical mechanism. This mechanism can be also applied in opposite way, meaning we can endow the exterior with the homogeneous isotropic metric, and interior with spherically symmetric static metric, and assume the same junction conditions. And again, but this is not surprising, because actually this is the same calculation. In this calculation, exterior, interior are not distinguished, the local calculation. So then again, this space-time outside determines the space-time inside, and again the same is true. So the second scenario is used for so-called the Swiss cheese model, which means we think of this region inside as the space in which space-time, part of space-time in which we are now, which is not expanding, right? We are not expanding now. As we are sitting in this room, the distances between us are I have comments from from the audience. We are not expanding here, right? On the other hand, we are all surrounded by some expanding universe. We learn from news, from press conferences. We learn from this, when we study physics, that we are surrounded by expanding universe. So in some sense, some non-expanding piece of space-time is glued together with expanding piece. So this is exactly this model, that this is this non-expanding part, but of course idealized. Suppose this contains our galaxy, and then this is outside is this expanding universe. So now it turns out that again the same mathematical mechanism works. If we fix this function A, introduce the junction conditions, then we obtain uniquely a function inside. And we can, this is a model which can describe Schwarzschild space-time put inside expanding universe. Because if we assume that this satisfies Einstein equations, then this what is inside becomes solution, becomes Schwarzschild solution. Hmm? You are the observer. Okay. Now, some small calculation. So here is the calculation. So on one hand, we have this geodesic curve, which in coordinates, those coordinates has very boring equation because everything is constant, only tau changes. On the other hand, in the strictly symmetric space-time, it has some non-trivial equation. T and R are functions of tau. And now if we require that this is geodesic in this strictly symmetric system, then we have several equations. One is just normalization of this. The first one, and tau, notice that tau is also the proper physical time of this geodesic as viewed from inside. So it means that for this geodesic outside, I mean, viewed from outside, it will be also a proper time. So we have normalization condition. Now we have preservation of energy because we have some constant of motion for each geodesic, which we can call capital E. Next, we can also but we can also use this standard procedure that we consider induced metric tensor. On this surface, there is induced metric tensor. There is second fundamental form. We can compare these induced metric tensors from the left and on the right. The second fundamental forms from the left, from the right. We obtain a little more equations, and at the end of the day, we obtain this fantastic equation. I mean, there are two important steps. One step is that a priori, here I allowed for different coefficients. So notice that this is not like in case of, there is somewhere here is -1, but the coefficient at dt square is not 1 upon coefficient at dr squared. Probably there are different functions. However, it turns out that actually they have to be the same modulo constant. And then after changing coordinates, we can turn this constant to 1. And at the end of the day, we obtain the following beautiful equation. So this is the function we are looking for, because this is this function here, and f already equals this function. On the other hand, here we have a dot in this expanding universe. And now either this is it, so then this function g is given just in some numerical way, but maybe we cannot in any clever way, more clever write it. However, very often if a dot is again a function of a, suppose it is of this form, h times a, then actually this will be the Hubble constant function. Then we obtain a nice equation that g of a, parameterized by tau, is h of a times a squared. R0 is here in this equation, it is a parameter, and originally it was the coordinate radius of this, the coordinate radius of this ball.
Okay, so this is the size of the system.
Right.
Okay, good.
Okay, so in this way we can really okay, so in this way we can really determine g. So this the classical Oppenheimer-Schneider, but we can also use solutions obtained by quantum models. Okay.
This calculation, little calculation shows it doesn't depend on Einstein equation. Right?
No.
So it applies to the dark, but it also applies to the solar system, basically.
Yes, yes. Yeah, this is the point, that here we didn't assume any dynamical equations. We have just two metric tensors, and this is true. Well, except that maybe if A dot turns out to be a function of A, then there should be A squared. Then usually this is given by some dynamics. This equality, but a priori. Mhm.
Because it's extremely interesting, I must say.
Yeah, I also like.
Because for many years, I was always puzzled by something that you already mentioned, that the universe expands, but the local system don't. There are many papers about it, all of them terribly messy and not really to the point. But this is a model which can explain this, because I understand that if you put the numbers of actual cosmology, you can actually see what is the maximal size of the system that does not expand along the universe because of local gravitational attraction.
Yes. So this is, but this is very well known model. It's called Swiss cheese model. Now we can just use it once again for spacetimes which are given by some quantum models, some semi-classical spacetimes given by quantum models. Yeah, but I also like very much this. Okay, so now the one ingredient of our construction here, this spacetime metric, will be, instead of the classical Lemaitre-Friedman-Robertson-Walker, it will be quantum, obtained by Ashtekar, Pawłowski, and Singh. So here I just extract from very complicated papers and complicated calculations some very simple semi-classical form of resulting metric. So it turns out that if you use this model, then in some sense, this model gives rise also to, in semi-classical regime, to a classical metric. It means metric described by continuous differentiable functions. The only difference is that this function A now, instead of satisfying the usual Friedman equation, which is given by this, and additionally, in this equation, we have another factor, which involves a new parameter, critical rho, and this rho is given by some constants of nature, and one more constant, gamma, which is constant of loop quantum gravity, which equals to this according to our calculation of black hole entropy, and to match it with Bekenstein-Holt. Now, what is the property of this spacetime? So in this case, A doesn't reach zero, neither in the past nor in future. It can be extended, so the argument of A can be extended from -infinity to infinity, and then A ranges from infinity to certain minimal value, which is bigger, sharply bigger than zero, and again grows to infinity. And this is this well-known bouncing effect of the Ashtekar-Pawłowski-Singh model, which here is described by the semi-classical metric, but it also is described in more proper quantum ways. So quantum states also are in much more complicated way that they satisfy this bounce. So now we are replacing this Lemaitre-Friedman-Robertson-Walker spacetime by this bouncing spacetime, and put it into and we put it here, and then we determine the Schwarzschild space. Then we determine something, and this thing which we determine, we call the modified Schwarzschild metric. Okay, so what we obtain is this. It takes the following form. So in addition to the usual term 2gm divided by r, we have another term which has opposite sign and which is proportional to 1 upon r to power 4. So it looks a little similar to Reisner-Nordstrom, however, here the power is different.
I would like to understand what you do.
Right.
You inside, instead of the description describing the dust with the standard Huggman model, you describe it with this modified model, so the dynamics inside is modified.
Yes.
But the rest is essentially the same. So the junction condition and stuff, everything is the same.
Exactly, exactly. So we go back to this picture. Again, inside we put the APS metric tensor, and then we let this nice mathematical mechanism to determine the metric outside. And what is determined outside we call the deformed Schwarzschild. And this is the form of the metric we obtain.
From quantum theory, you get specific function A, or
Okay, so once again, from we get from what we get from APS model, we get function A which satisfies this equation, and there is still continuity condition satisfied, and then we can just solve. And the authors of this paper they solve this equation and they can write explicitly A. I just didn't write it, but I could, if I check better, I would find in their paper. So what is quantum here is this rho c. If the world is classical, then rho c equals infinity. If we believe in Ashtekar-Pawlowski Singh model, then rho is not infinity, and some effective semi-classical spacetime which emerges from this satisfies this equation, and A is a solution to this equation. So we can see that S rho is very is much smaller than, so this rho c is quite big. This is quite big number, and now rho is very small. Gamma is 0.23.
But why you denote this by letter?
This is
Square root of 3, you don't denote by letter.
This is
numbers are numbers.
This is a parameter of loop quantum gravity, which is fixed by consistency with the Bekenstein-Hawking entropy. There is also debate about what is the value of gamma. There are some other models according to which it's a little bigger, but I would say it's between 0.2 and 1. So it's the range. Maybe other models predict 0.27 or 29. I don't remember.
G squared times h bar is big, because normally G is small and h is small. So why is it big?
Okay, probably there is also
G8 is Planck scale, right? If G8 is the G8 is a Planck.
What is G? G is a gravitational constant. So usually it's very small.
it's there is this.
Okay, so this is very small in so rho is big.
Yeah, rho critical is big. You have to imagine
Very
that
small numbers.
that classical infinity was replaced by some finite but big numbers.
I
So
missed slash.
yeah, so if rho is realistic like now, then this number is negligible, and we have the Friedman equation. But if we get close, if we go backward in time, closer to when the universe was squeezed, then at some point the rho reaches value of rho c, and then we obtain 0, and then the evolution stops. So then A has minimum, and then it bounces. Okay.
Rho C is essentially Planck mass divided by Planck length cube.
Yeah, modulo some
Modulo some.
factor which is there, maybe, which is not too big. Okay, so we put this metric. So actually we didn't have to solve this equation. It was just enough to know this equation, and then due to this equation, as you see here, it's enough to know what is A dot. You don't even need to know what is A itself. So due to this, we are able to calculate the modified Schwarzschild metric, where alpha is this, and one should emphasize that this spacetime, that this metric is determined only where in the range of A, because since A doesn't shrink to 0, A bounces. So in fact, it's determined only for parameter for coordinate r bigger than r of the bounds. So there is still some region in which our calculation doesn't determine the metric. It can be anything what we want to be, or what is given by some other data.
Could you explain what you're saying? Because I understand that inside you have the metric, outside you have your at any time. Outside you have this modified metric.
Right.
So why are you saying that it's something that is really not determined?
It will be clear on next slide, where I give global structure. I will depict global structure of it. Okay, so we will go back to this. It's not, we didn't check all the properties. We just checked how much is energy, for instance, and it will be in one of the next slides. It is an energy is positive. Energy is positive. That we didn't check, but this is a two-line calculation, so we can check, or maybe its own knows. Right? So, and this is the radius of the bounds. So actually, this metric was derived in several papers in literature. Sometimes it is derived from different assumptions, which is interesting. So from completely different assumptions, it means that you consider a strictly symmetric spacetime, quantize this spacetime, and then find semi-classical metric corresponding to, semi-classical metric corresponding to this quantized. And then it turns out you also obtain this. That was in sense, this is seems that this result is quite robust. It follows from various assumptions, various models, but in particular we also derived this metric in paper by Parvizi, Pawłowski, Towakoli, and myself. However, in that case, we considered not only this space-time, this homogeneous and spherically symmetric space / spherically symmetric, but we also considered a quantum mode, which induces some back reaction, and we even calculated the back reacted metric. But if you set this to 0, this quantum mode to 0, then we obtain the same metric as here. So this completes the first part of which. So I go back to our question. We want to know what is the fate of black hole, of collapsing matter, in case when we take into account quantum models describing black hole interior. So
sorry for asking so many questions, but that I think it's important. What is M?
M is mass of M. So we do the following. We write rho. So we have for rho, we have continuity equation. And this equation is the following, that rho times a cube equals constant. So we call this constant m divided by 4 by 3 pi r0 cubed.
So this is not a dominated universe itself, right?
Yeah, this is thus dominated, and then the same m now shows up here, and here we already can give, we know what is m. M is the ADM mass of this. So if we are far, then this term is negligible. This is just ADM mass of this space. Okay, so we calculated such metric earlier. However, we didn't know what was the global structure of this spacetime. So this furnishes the first ingredient which we need to answer this question. So we, using this Oppenheimer-Schneider model, we calculate this spacetime. Oh, but now we can already, so now we can start analysis of this spacetime. Well, we can start analysis of what we have. To start with, we can see that this coefficient has roots only when mass is bigger than certain minimal value. So we can call it a lower bound of the black hole mass that can be obtained by using this model. Now, if m is bigger than m minimal, then there are two roots. And well, those roots can be, if we introduce some extra parameter b, they can be written in such way. And there is also extremal case when m equals m minimal, and in that case, we have extremal modified Schwarzschild. And then this, but of course, in this case, this
So how much is this m minimal?
This is here.
Yeah. You can compute it.
Okay, this is Planck length, and
Solar mass is how much?
no, this is some microscopic. This is basically Planck mass times some numerical coefficient which is not big, which may be 20, maybe 1 upon 20, but not much more. So it's of the range of the range of the scale of the Planck mass. So certainly some very small mass. Okay, so let us consider.
If the mass is smaller, then there will have a white hole, right?
No. If mass is smaller, then this ball doesn't collapse. I mean, doesn't create black holes. So ball collapses, bounces, but horizon doesn't form.
Oh, that's fine. So this is kind of a Reynolds problem.
So yes. Okay, so now let us consider generic case when their mass is bigger than minimal mass, and when there are two horizons. So now we can analytically calculate. So we can just assume this spacetime, and we can calculate maximal analytic extension in a similar way as Kruskal did, and then we obtain such diagram which is very similar to Reisner-Nordstrom, which means here is, for instance, one asymptotically flat region. Then there is a trapped region between the two horizons. Then if we extend this spacetime also to the oh, and now I will be able to answer your question. So this red dashed curve is exactly the junction surface. So now this spacetime actually admits only one location for this junction surface, modulo symmetry, which is symmetry is time translation. So we have only one junction surface modulo symmetry. And now you can see, now in the past infinity, this surface is tangent to the killing observer in rest. So one can say that in infinity, this ball is infinitely large radius, and it is in rest. Then it collapses. However, it collapses to certain finite value. It doesn't collapse to zero. It bounces. So our junction conditions, they are well defined only for R, going from infinity to the value at bounds. But our junction conditions don't hold for R smaller than, because they hold only at the point of the surface, and the surface never goes below R equal R bounds. So that's why we can determine everything only for R less than infinity but bigger than R of bounds. Okay, so this is the global structure, but let us now explain. So this is the junction surface. And this junction surface, as I said, it's unique in a sense that asymptotically is tangent to the static observer. This is the bounds. And we have those regions A are static and asymptotically flat. So we can think that we are now in one of those regions. These are trapped regions. And these are, additionally, they develop two static, we can call it wormhole regions. And that spacetime is determined for R bigger than RB. However, if we want, we can extend it analytically by analyticity to smaller R, as we do when we define a maximally extended spacetime. However, then even if we extend it, then we have this time like infinity, similar to infinity in Reisner-Nordström. But then we have also the same effect as in Reisner-Nordström, that for a physical material point, it is impossible to reach infinity, because the energy, you would need infinite work to do. Sorry, so there is singularity at R equals 0, and in order to reach the singularity, you need infinite work. So all geodesics bounce earlier, but even non-geodesic, okay, so there are time-like curves that reach the singularity. However, you need infinite work in order to physically implement such curve as trajectories. So in this sense, this singularity it has different character than Schwarzschild singularity. And okay, so, and the space-time outside, and all this space-time has this form. And now the partial answer to Jacek's question. So we can now calculate T mu nu, and we can calculate the energy density, which from the point of view of the static observer, and then static observer can see this energy density. So if we are brave, we can even call it dark energy, dark matter. However, we don't have any guarantee that this formula reproduces the properties of the non-dark matter. But if this model was true, then indeed the observer outside would feel some curvature of space-time, which observer would interpret as some matter. However, there is no matter. This is just effect of quantum gravity coming from inside. So now let us go back to the Oppenheimer-Schneider model. So here we have this. So outside we have this modified Schwarzschild. Inside we have this quantum Lemaitre, Friedman, Robertson, Walker. Okay, so suppose that we stay outside, that we never enter the space-time where the ball is. So suppose we are. So that would mean that we are somewhere here, And then we can see there is this collapsing ball. Okay, I can even, so this is the collapsing ball. And we are a static observer. Okay, maybe this ball passed us somehow, but then later we are a static observer. We observe that there collapses a ball, that develops horizon. And this is it. If we don't enter the horizon, we are not going to learn anything more. And we can complete our existence we can live infinitely long and not being aware of something happening inside. This is the event horizon. So a static observer will never see the bounds inside the horizon. They will only observe this dark matter. Okay, now suppose that we are in a different asymptotically flat region here. Then we will see a white hole, and I copied this, I think, from one of the papers in which the similar phenomenon is described: tsunami of dust that will flow out of the black hole, of the white hole. So here we will see only white hole, but we will not see black hole on the other hand. So we will not have black hole, white hole transition. We just have white hole and a lot of stuff flowing out. However, there are also available some other regions. We can jump inside and we can. So here, interesting result is that the space-time develops in such a way that even though the minimal radius of collapsing ball is the radius of the bounce, actually we can also have access to the radius smaller than bounce, at the same time stay outside the black hole, never sink, never dive in black hole. So if there is singularity there, we will see the singularity. On the other hand, we can also consider the quantum Swiss cheese model. So then this is opposite scenario. So our deformed quantum modified Schwarzschild spacetime is here. And then outside there is this quantum universe, which is surrounding our, say, galaxy. So now we would be here. This is asymptotically flat region. And this is the end of this red line is the end of our bubble. And this is where our bubble, so this is our bubble, which is vacuum, modulo this dark matter. And this is the end of this bubble, and behind this bubble there is quantum universe and the matter of the quantum universe. And here in our part, this universe is expanding. Sometime in the past, this universe was contracting. And we can think of ourselves as a static observer here. And then the spacetime contains both black hole and white hole horizon on the same basis as Kruskal, as in Kruskal spacetime. We have spacetime extended all the way such that the white hole horizon also develops. But there is also another possibility for static observer. So this is static observer in this different phase of universe when universe was contracting. So then this observer would see a contracting universe squeezing his bubble, would see universe squeezing their bubble. So then at some point the observer may either let the universe cover this way, or can stay in the bubble, and then would be black holes, that there was some bubble in the past that didn't want to be black hole at all. However, it was squeezed by this universe. So universe produced a black hole, and now we have a black hole here. And again, this modified Schwarzschild, from the point of view of classical Einstein equations, it is not vacuum, but it defines some energy density, and this is once again the same energy density, which can be thought of as the dark matter. So this is it. Thank you. I'm sorry for not having the last transparency with thank you and yes.
I already have so many questions, but the last one.
Mhm.
Did you consider the influence of Hawking radiation? It seems to be pretty easy to implement.
Yeah, this is fantastic question, and indeed, people try to combine Hawking radiation and this mechanism. Here, this mechanism was somehow isolated from Hawking radiation. So I didn't consider, but indeed, there are results also on Hawking radiation, and I also think that that in this talk, which I have seen at Loops, which was by Michał Bobula, actually he considered since he considered basically the same model, he also considered their Hawking curve. So maybe.
What is affiliation of
Wrocław, Tomek.
Other questions?
I have a question about some junction conditions. Some more general question. Suppose we have two different regions. One metric is spherical symmetry inside, and the surface of so we have one spherical symmetry inside and another outside, and we have some gluing conditions similar to this. But we don't assume anything else, because then you can also have some relation between those functions, which are functions of two variables, R and T.
So what
Because
is
there is canonical form of the spherical symmetric metric inside and outside. And what you get in this general situation, without assuming that outside is something static or
right?
There's also some relation, yes?
Yeah,
So,
yeah.
Which means that if something is inside fulfills equations, then outside you don't guarantee that it fulfills equations.
Right. So here we didn't have to assume it is static. Here, if we could assume, I mean, but then we wouldn't obtain this result. One could assume, one could allow here metric that is strictly symmetric but is not static. And then we have some
but then you have more freedom.
Then
you can produce this dark matter in some sense, because it depends on time, and then maybe you can adjust this model to the cosmology. This is
yes, that's true. Yeah, that's true. But it is nice to see in the zeros order what is determined by the mathematics, and but you're right. One could assume that there is some time dependence, and then and then we would have ambiguity in what we obtain. So either we could assume something more about the outside, or we would have much more. Yes. So there's also possibility of generating, of defining similar model, but with non-static spacetime outside.
So it is not very relevant to talk about IT. I always get a little unpopular when people never know the numerical value that we use because on one hand, we Spacetime Hawking formula for the entropy Newton. So there's the value of Newton constant at low energy. And then in the area spectrum, we have usually especially when we have Newton constant at the one scale. And then we also do normalization, we use two values that are not the same as these. I don't know if the same value that we normalize by
Right, right. Yeah, but then there are some other models in which they consider cosmology with effects of loop quantum cosmology, and then the numerical results they obtain depend on what we choose for gamma, and from those results it follows that anyway, for the other models to be correct, this gamma has to be more or less up to maybe before between 0.19 to 0.32, but not more. Or maybe this accuracy is even better. So, but of course you can always say that the quantum models they consider are could be replaced by some other quantum models. So certainly there was no conspiracy. They just considered this APS model and the Ashtekar bias Krasnov black hole model and not knowing that is going to happen. This number 0.23 seems to fit well within the error of observations. So actually, even Abai even thinks that this is a beautiful coincidence. However, some other people who introduce different models, for instance, with this Timmans term in Hamiltonian instead of curvature or vice versa, then they say that they obtain that if their model is applied to cosmology, then they obtain different interpretation of the observational results, and then there again maybe gamma can be fixed differently. But thus far it seems that this ambiguity is not factor of 1,000. That this ambiguity is much smaller factor, closer to 1 to 10.
You never know if going to the low energy scale, this running G that will cancel gamma at all. So for large black hole, for classical black hole, if you compute the entropy, then it may not depend on gamma at all, as a classical calculation actually indicates.
Yes, I agree. This is the standard argument of people who do renormalization, that our G is a Bayer G rather than renormalized G. That perhaps in loop quantum gravity we thus far don't have this renormalization of those. However, we compare to Bekenstein-Hawking, which is true, which is somehow from. Thank you.